Welcome to The Explainer. Today we're talking about an invisible force that's absolutely essential for pretty much everything that spins and moves in our world.
So take a look at these two incredible machines. On one side, you've got the raw power of a car's drivetrain. On the other, the life-saving lift from a helicopter's rotor. What's the hidden connection here? Well, believe it or not, it's not just about the engine. There's a fundamental force at play, a principle of twisting that makes both of these things even possible.
And the answer is torsion. It's all about the physics of twisting. You can think of it as an invisible workhorse, constantly transmitting power in everything from a simple power drill all the way up to those giant wind turbines that power our cities.
So today, we are going to untwist this whole topic. First, we'll dive into what torsion actually is. Then we're going to visualize what's happening deep inside the material. After that, we'll get into the physics behind it all, see how engineers use this knowledge to design things that don't break, and finally, we'll connect it all back to how this simple twist puts real power into motion.
All right, let's jump right in. Section 1, the world of torsion. So what exactly is this twisting force we're talking about? In the simplest terms, torsion is just what happens when you twist something. Now, engineers have a specific name for that twisting force. They call it torque. So anytime you see a long, round object that's designed to spin, like a drive shaft or an axle, you can bet torsion is the name of the game. Picture this. You're wringing out a soaking wet towel. You grab both ends and your hands twist in opposite directions, right? That is the perfect picture of torsion. It's this opposition, this twisting battle between the two ends that puts the entire material under stress from the inside out. Okay, so we're twisting it, we get that. But what's really going on inside the material? I mean, to the naked eye, it might not look like much is changing. But trust me, on a structural level, there's a whole lot happening. Let's visualize that twist. Okay, so let's imagine we take a simple shaft, and we draw this perfectly straight, square grid on its surface. You can see the lines running down its length are parallel, and the lines wrapping around it are perfect circles. Everything is nice and neat.
Now let's apply that torque. Look what happens. The straight lines, they're now warped into these cool-looking spirals. But pay close attention to what doesn't change. The circles, they're still perfect circles. Now this might seem like a tiny detail, but for an engineer, this observation is an absolute game changer.
And here's why that's so important. The fact that circles stay circles means the shaft isn't bulging or warping out of shape. And because of that simple fact, the math to predict how it will behave becomes a whole lot easier, which allows engineers to build things that are safe and reliable.
So, how do engineers measure this twist? Well, they use a precise measurement called the angle of twist, and it's usually represented by the Greek letter phi. It tells them exactly how much one end of the shaft has rotated compared to the other.
Okay, so we can see the deformation, but how do we actually quantify it? How do we put a number on the stress it's creating inside that material? Well, that brings us right to the physics of strain. Now, I know this formula might look a little intense, but the story it tells is actually really simple. This shearing strain basically depends on just three things: how far you are from the very center of the shaft, how much that shaft is being twisted, and of course, how long it is.
So, what does this all boil down to? It's this. The twisting effect is literally zero right at the core of the shaft. But as you move outwards towards the edge, it gets more and more intense. All the action, all the stress is concentrated right there on the outer surface. That's the part of the material that's doing all the heavy lifting.
And knowing that, well, that's absolutely critical for engineers. Understanding that the maximum stress is always on the outside surface is fundamental to designing parts that won't, fail. This is where things get really practical.
You can actually tell a lot about a material just by how it breaks under torsion. So something ductile, like steel, it can stretch and deform so it eventually fails in a clean, straight line. But brittle materials, like a piece of chalk, they can't handle being pulled apart. The twisting creates this tension at a 45-degree angle, and that's exactly where they snap.
And it's not just the material. Shape is a huge deal. The circular shaft is the undisputed champion of handling torsion. For the exact same amount of material, it can withstand over 37% more torque than a triangular one. And that incredible efficiency is why you see round shafts pretty much everywhere. They give you the most strength for the least amount of weight. So let's bring this all back around to where we started and look at how torsion is actually used to transmit power, because that's its main job in most machines. Just think about any system where rotation creates power. A power plant is a perfect example. You've got this massive turbine spinning.
driving a generator. The connecting shaft is the real hero of that story. It's under constant torsion, taking all that rotational energy from the turbine and delivering it right where it needs to go to make electricity.
And the link between that torque and the power you get out is super direct. A torque makes the shaft spin. That spinning motion performs work. And the rate at which that work is done, that's what we call power. It's a pretty simple relationship. If you want more power, you either need more torque, more speed, or a bit of both.
And it all comes down to this single powerful idea. This principle connects that twisting force directly to the useful power a machine can produce. It's how an engine's grunt gets to the wheels of a car and how it gets to the blades of a helicopter.
So, from the engine roaring in a supercar to the silent spin of a wind turbine, torsion is that incredible, invisible force, turning a simple twist into the work that powers our entire world. Understanding it is fundamental to understanding how things move. So the only question left is, now that you can see this invisible force, what will you build with it?